The periodic table is a marvelous and fundamental discovery for understanding the chemistry of inanimate and living matter. This presentation will introduce the concept of superheavy elements, which have been recently discovered, and compare their properties to regular elements in their group. The initial periodic table of elements was created by Dmitri Mendeleev in the late 1860s. Around the same time, others such as Newlands and Mayer were also working on such a table and had realized that some groups of elements have similar properties. Mendeleev was unaware of their research, and his table had more elements than theirs. He also was able to accurately predict the properties of some of the heavier elements. The periodic table was created on the bases of groups and accurately captured patterns of behavior. For example, the elements in the last group of the periodic table, group 18, are called the noble gases because they all are inert gases and have a filled electron shell. The oxidation states of elements in a column or group are usually the same. Properties also vary across the rows because of the dependence on atomic number. The formation and existence of superheavy elements rely on nuclear chemistry. Radioactive decay is a process by which an unstable nucleus loses energy in the form of radiation, and another more stable nucleus is thus created. However, the new nucleus is not necessarily completely stable. The fission process is one in which a nucleus splits into two smaller daughter nuclei. A fission reaction can be triggered by a slow neutron incident on the mother nucleus. If the reaction produces more than one neutron, then these can trigger other fission reactions, leading to a chain reaction. A fusion reaction is when two nuclei fuse to form a larger nucleus as a product of the collision. The condition needed for fusion to take place is that the nuclei have sufficient energy to overcome Coulomb repulsion and the energy barrier to initiate the nuclear reaction. Typically, this requires a very high temperature, as in the sun. The nucleus of an atom is made up of protons and neutrons. As the number of protons increase, there is a need for a larger number of neutrons to counteract the repulsive force of the proton-proton interactions. The neutrons provide the glue that holds the nucleus together. Therefore, the proton-neutron ratio decreases as the atomic number Z increases. The island of stability is a theorized region in which the magic number of protons and neutrons combine to form a stable nucleus. There are two dominant mechanisms for the creation of superheavy nuclei: fusion of two regular nuclei and decay of a mother superheavy nucleus. Group 13 consists of boron, aluminum, gallium, indium, thallium, and ununtrium. Boron exhibits a nonmetallic character, whereas the rest are soft metals. They all have an oxidation number of 3, but thallium exhibits both an oxidation number of 3 and 1. Element 113 was jointly discovered in Lawrence Livermore National Laboratory in California and the Joint Institute for Nuclear Research in Dubna. Their discovery was published in 2004. They created element 115, which decayed into 113. 6 isotopes have been found. All are unstable and decay within 20 seconds. A surprising property of element 113 is a marginal electronegativity, which is unusual because electronegativity typically increases as one moves up the periodic table and is often close to 0 at the bottom of the table. Group 14 consists of carbon, silicon, germanium, tin, lead, and ununquadium. This group is diverse in that the states range from nonmetals to metalloids to metals. They all have an oxidation number of 4, but a few also have an oxidation number of 2. The elements are not very reactive. Element 114 was jointly discovered by people in Lawrence Livermore National Laboratory in California and the Joint Institute for Nuclear Research in Dubna. Their discovery was published in 1999. They created the element by a fusion reaction of plutonium-244 and calcium-48. 4 isotopes have been found. All are unstable and decay within half a second to form element 112, cupernicium. Element 114 is thought to have noble gas-like properties, which is unusual because it is a group 14 element. Group 15 consists of nitrogen, phosphorus, arsenic, antimony, bismuth, and ununpentium. Group 15 consists of very toxic elements. The elements at the top of the group are stable because of the double and triple bond they form. Element 115 was jointly discovered by people in Lawrence Livermore National Laboratory in California and the Joint Institute for Nuclear Research in Dubna. Their discovery was published in 2004. They created element 115 by the fusion reaction of calcium-48 and americium-243. 4 isotopes have been found. All are unstable and decay within 300 milliseconds. Not many properties of element 115 have been studied, but it is theorized that it will have an oxidation number similar to that of bismuth.
Group 16 elements include oxygen, sulfur, selenium, tellurium, and polonium. At STP, oxygen is the only gas in the group 16 elements. Other than oxygen, the group consists of metalloid semiconductors, which means their electrical conductivity lies between conductor and insulator. Polonium was infamously used to assassinate Russian spy Alexander Litvinenko in November 2006 because of its high radioactivity. Polonium enjoys having the most isotopes of any element on the periodic table. Element 116, ununhexium. Ununhexium was discovered on July 19, 2000, formed by the fusion of calcium-48 and curium-248, yielding UUH-296, which decays quickly into UUH-293, its most stable isotope. Its half-life is around 60 milliseconds, and is expected to undergo oxidation to a dioxide and should have a stable +2 oxidation state. Group 17, a highly reactive group, the halogens include fluorine, chlorine, bromine, iodine, and astacine. Chlorine and bromine are often used as sterilizing agents for wounds or disinfecting agents to kill bacteria. All of group 17 readily combine with H+ to form acids. Their melting point rises as you go down the period. Element 117, formed by the fusion of calcium-48 and berkelium-249, yields unobseptium-297, which decays into UUS-293. It was published by the Dubna team in April 2010. Although not much is known about its chemical properties, it is expected to show metalloid characteristics. Group 18, as noble gases neon, argon, krypton, xenon, and radon are largely unreactive, and at STP all exhibit no color or odor. The melting and boiling points of the gases differ from each other by less than 10 degrees Celsius. Helium in its liquid state below 2.17 Kelvin becomes a superfluid, a fluid in which heat conductivity is perfect and its entropy drops to 0. This is the only substance known to display this behavior. Element 118, ununoctium, formed by the fusion reaction of krypton-86 and lead-208, yields UuO-293. Although in the group of noble gases, it is expected not to show noble gas properties. It's predicted to be a solid under normal conditions and to show the widest polarizability of all the elements. This map shows the discovered elements on a plot of proton to neutron numbers. It deviates from the 1-to-1 ratio observed in lighter elements. Just beyond the area of known elements lies the much anticipated and theorized island of stability. The island of stability was predicted by Nobel Prize-winning Glenn Seaborg, who died in 1999. He played a critical role in discovering 10 elements, the most discoveries of any human. He proposed that the nucleus was constructed of shells, much like the electronic structure of atoms. There would be certain magic numbers that were extra stable, which would yield this island of stability. Most notably, ununhexium 310 would be superstable because of a special combination of so-called magic numbers. Any element found past 118 would constitute a new period to the periodic table and whose implications would allude to the existence of a G block and G orbitals. This is where the center of the island of stability would be.
Science is the best tool ever devised for understanding how the world works.
Science is a vehicle for knowledge. We are always at the brink of the node. Science is a collaborative enterprise spanning the generations. We remember those who prepared the way, seeing